So we're going to be starting a new chapter on mechanical properties, chapter 6. So the issues addressed in this chapter are, first of all, the concepts of stress and strain. So what are stress and strain, and why do we use those instead of the load and the straight-up deformation of the material? We're also going to talk about elastic behavior, and this occurs at small loads, and then how much deformation occurs for a small load, and what materials deform the least, and what are the limitations on that. We're going to discuss those concepts in today's lecture. Next, we're going to talk about in the chapter plastic behavior. At what point does permanent deformation occur? What materials are most resistant to permanent deformation? And finally, we're going to talk about toughness and ductility. What are they and how do we measure them? So today's lecture, the subject of it is elastic deformation. And so elastic deformation is deformation that's not permanent. So in other words, you have a material, it's initially got some configuration to it. You apply a small load to that material. That causes a stretching of the bonds, say, but then when you release the load and you unload the material, it returns to its initial configuration. So you're not permanently changing the material, you're just kind of briefly stretching it out and then it goes back the way that it was, kind of like a rubber band. And so this is a linear regime, a linear response. You have a force applied and then there's a small deformation of the material. It's very similar to the idea of Hooke's law, F is equal to K delta X, for masses applied to a spring when the weight pulls down on the spring and then the spring returns to its former behavior, and it can be modeled in that way. Now this is as opposed to the other kind of deformation which occurs in metals and polymers, plastic deformation, where you apply a load. It's initially in some configuration, then you apply the load. It causes the bonds to stretch, but it also causes the movement or dislocation of atoms with respect to one another. And once those atoms have moved, right, once the shearing has occurred, then it doesn't go back. Okay, so plastic means a permanent deformation of the material, a permanent change in the material. And of course, this looks very nonlinear if you plot the force versus the displacement of the material, how much it stretches out. It doesn't go in that linear or elastic regime, it has a curve to it. Okay, so this is a non-linear response of the material. Okay, so let's define the concepts of stress and strain. Okay, basically the idea here is that if you're in that elastic regime, how much force it takes to deform the material is a little dependent, or actually no, a lot dependent on how fat the material is, right? So a small load, for example, will deform a big fat thing hardly not at all, but that same amount of weight will deform a small thing by a lot. Okay, it'll stretch out a lot. It's kind of the difference between having a very thin wire and a very thick wire and applying the same weight to it. Okay, so what we want to do to normalize for that effect and only think about what effect the material itself has and not its dimensions is we want to divide out by that cross-sectional area, and that brings us into the idea of a stress. Okay, so a tensile stress, often symbolized with a sigma, is defined as the force that's applied to the material in the tensile direction, which is along the axis, along the long axis of the material. Okay, so if you have a wire that's long in this direction, a tensile stress is applied where the force is applied in the same direction as the long axis. Okay, so that force divided by the original cross-sectional area of the material before it's been loaded. All right, this can be in English units, pound per square inch, or in SI units, newtons per meter squared. So oftentimes this is expressed in terms of pascals. Remember that 1 Pascal is 1 Newton per meter squared, and Pascal is abbreviated PA, capital P, lowercase a. Okay? You can also apply stress in other directions. So for example, if you have a material and you apply the stress this way to the material, that's called a shear stress. The symbol for shear stress is a tau, the Greek letter tau. And so what you do is you take the force that's applied along the perpendicular axis here, this F sub s, and you divide by the cross-sectional area of the material A. Now, In any device, you could have any number of different kinds of stress. So this is an example that's pretty familiar to those of us that live here in Boone. It's a ski lift, all right? So the cables on the ski lift are under tension. So they're being pulled tight, okay? That's a tensile stress. And then the shaft here, which is helping to rotate the cable, is under a torsional stress, which is a form of shear. So for example, drive shafts are often under a shear stress. And it's kind of like doing this to the material constantly, where it's being, torqued one way on the top and the other way on the bottom, okay? So that's torsion. So that's the same kind of thing, and in any given device, things can be under both shear stress or tensile stress, depending upon what the device is like. Some other common stress states are compressive stress. So for example, this is common in bridges. You have to worry about not being pulled this way, but being pushed on from either end. Okay, that's a compressive stress. And also, you can apply sort of a volumetric pressure to something. So, for example, if you are in a submarine and you're going down to really strong depths, you're under hydrostatic compression. Your submarine is being pushed in from all sides. Okay, that causes a change in volume, trying to push the volume, make it smaller. Or you could have something like a gas cylinder where the gas is pushing outwards on the material and trying to get it to expand. Okay, and that's biaxial tension. Pressurized tanks, really common example of that. So those are some of the different kinds of stress that a material can be under. So what happens to a material in the presence of a stress is called a strain. A strain is a dimensionless quantity, and it's a change in the length. For example, if it's under a tensile strain, it would be the total amount that the material stretches out, delta, from its original length, which is here called L naught. So strain is a dimensionless quantity. Strain is always dimensionless, and it's the change in the length over the initial length, and it's often symbolized with an epsilon as it is in your text. You've also got a lateral strain, okay? So if something gets longer, for example, stretched out this way, then it also might get thinner, okay? So what dimension increases, the other one is going to decrease in that material. So the lateral strain is given here with a negative sign to show that you've got a change that's opposite in sign to the tensile strain, and it's epsilon sub L is equal to, and this is the change in the lateral dimension, delta L, divided by, here W naught is the initial width. Okay, so that's the two strains for that. If something's under a shear, then that is going to cause it to change its angle. So oftentimes we use the tangent of the angle, tangent theta. That's how much it's gotten sort of torqued, if you will. That angle theta is how much it was torqued. And that is the change in the x dimension divided by the initial y dimension component to give you that angle. We're going to do a lab on stress strain testing. We have a tensile testing machine here in our building in Garwood. It's on the second floor. We'll do one of our labs on that. Basically how these devices work is you have your specimen and you have some kind of sensor in there to measure how much the material stretches, and then you just apply a load, an increasing load, pulling it apart, and watch what happens to material behavior as you apply that increasing load, measure the strain, in other words. So we'll do that for a lab. All right, like I said, this is a Hooke's law kind of idea. If you're in the linear regime and you haven't begun to permanently deform your material, then you're governed by Hooke's law, which is similar to the force on a spring. So put Hooke's law in terms of some of our symbols that we're using here. The force would be equal to K times delta, where delta is the change in that length, similar to K delta X for Physics 1150, 1151. Now, in terms of the strain, epsilon, delta would be equal to epsilon times that initial length, okay? So Hooke's law could be written, F is equal to K epsilon L naught, where K is that spring constant in the material. Now, let's look at it, Hooke's law, in terms of what it would be for these bulk materials. Instead of a force, like we talk about in Physics 1150, 1151, we want to talk about a stress, which is a force per unit area. So we would take that Hooke's law force, K delta, and divide it by the cross-sectional area A. And then plugging in, we'd have K epsilon L naught over A. Now there's a property that is a material property, and it's called the Young's modulus or the elastic modulus, often symbolized by this uppercase E in your textbook. In other textbooks, sometimes they use a Y for Young's, but here you go. There you have it. All right. So this is the modulus. Now the modulus of the material you can kind of think of as the stiffness of that material, how resistant it is to a force, right? Kind of like a high spring constant material would have a high elastic modulus as well, very resistant to a stress, an applied stress. But instead, it's been normalized to get rid of the dimensions of the material and focus in just on the material properties, okay? So this modulus E is going to be proportional to this spring constant or stiffness sort of the bonds of the material, and then normalized out for the dimensions of the material. So it only depends upon the material properties, okay? So Hooke's law, written in terms of material science, would be sigma is equal to E epsilon. So what you can do, and what we'll do in our lab, is we'll monitor what happens with stress, how much strain is resulting in the material from that stress, and then from the slope of that line, we'll get the elastic modulus of the material when it's in the linear regime. So the slope of your stress-strain plot is proportional to the elastic modulus. It's normalized for the material, so it really depends upon only the bond strength of the material, how strong those bonds are, and how much they're willing to deform. Okay, let me do an example problem for you. Here you have a cylindrical specimen of a titanium alloy, and it has an elastic modulus of 107 gigapascals and an original diameter of 3.8 millimeters. And it's going to experience only elastic deformation with a tensile load of 2,000 newtons is applied. Compute the maximum length of the specimen before deformation if the maximum allowable elongation is 0.42 millimeters. Now this is the kind of engineering problem that material scientists sometimes face. They've got a maximum allowable amount that this material is, allowed to move. And so from that, they need to figure out how long they need to make their material given the elastic modulus of the material. All right, so we're going to use the formulae that we've already been talking about. Here we have sigma is equal to E epsilon. A gigapascal is 10 to the 9th pascals. So here we have our elastic modulus plugged in, 107 times 10 to the 9th pascals, times our strain, epsilon. Now, sigma is our stress, and the stress is the force per unit area, okay? So the force here is 2,000 newtons, and then we're going to divide by the cross-sectional area of the material. The cross-sectional area of a cylinder is due to a circle, so that's pi r squared. So you have pi times 1.9 millimeters squared. Now it's 1.9 millimeters because the diameter was given and not the radius, and so we need to divide by 2. So you have 2,000 divided by pi times 1.9 millimeters squared, and then when you solve for that, you get your stress, which is 1.76 times 10 to the 8th pascals. Now, your strain is, when you solve for that, plugging in for your stress and for your Young's modulus, you can solve for what your strain is supposed to be via that sigma is equal to E epsilon relationship. And we solve for our strain and we get 0.00165. And this is equal to the maximum allowable elongation, as said in the problem, was 0.42 millimeters, and then divided by the initial length. The initial length is what you're solving for here. So you do a little cross multiplying and you solve for that, and you get 255 millimeters or 2.55 meters. All right? Okay, there's another parameter that's often given for a material. It's called the Poisson's ratio. And that's because, as we discussed, if you elongate something in one direction, say here Z, then that causes constrictions or also strain in the lateral directions. And these are related to one another by a negative sign. In other words, if it gets longer in Z, then to compensate, it's got to get narrower in X and Y. And so here your Poisson ratio is going to be the ratio of the strain in those two directions. In order to make it a positive number, you put a negative sign here up top because remember, a negative strain in one direction is a positive strain in the other. So here you have the Poisson ratio, often symbolized by the Greek letter nu here, lowercase Greek letter nu, is equal to minus the strain in the X direction divided by the strain in the Z, or minus the strain in the Y direction divided by the strain in the Z. So it's just a ratio of the strains in the two competing directions. Now here we can see that your Poisson ratio for typical materials, metals about a third, ceramics about a fourth, polymers about 0.4. So these are relationships. Again, it's a material property, so it's something that could be given for a specific property. For example, you might look it up and say, oh, what's the Poisson ratio for gold? And it would have a certain value there for gold, maybe even given as a function of what kind of alloy it is, what carat the gold is. Okay, so you could find that information out. Now the threshold value here is about 0.5. If your Poisson ratio is greater than 0.5, then that means your density increases. Now you can see that typically that's not what happens for these materials. Metals, ceramics, and polymers have Poisson ratios that are less than a half, okay? And what that means is if your Poisson ratio is less than a half, then that means that your density decreases. Basically what that means is that you're getting voids within your material, okay? You're creating voids. Now why a half? Why would a half be that threshold value here? Well, that's assuming that half threshold assumes that volume is conserved, which is not true. That's not a law of physics, but let's just assume that it is for a second. That means that if the stress is applied, the material gets thinner and longer, okay? So here's a slice through that, and it shows the material getting thinner as you stretched it out. The blue is kind of after, and the green square on the outside is kind of before, and then of course the material got longer. Now if volume were conserved, let's say that it was a square cross-section, so that its old dimensions were x squared times z. That was its initial volume. And then when it deformed, it lost material in the x direction, so you had x minus delta x, and then that gets squared to compute the volume, but it gets longer in the z, so you have z plus delta z. Now if volume's conserved, you can set this initial value equal to the final value, so that's what I've done here, okay? And now I've expanded that x minus delta x term, so you have x squared z is equal to x squared minus 2x delta x plus delta x squared, and then times z plus delta z. Well, what we're going to assume is that these deltas are pretty small numbers. Like, let's say that it only changes by 0.01 millimeters. Well, if you multiply a 0.01 millimeter change times a 0.01 millimeter change, you have something that's pretty vanishingly small. And so we can neglect these delta terms that are squared, okay? So that goes away. It's basically 0. So that takes us to this next line here where that delta x goes away to 0. Now I'm going to go ahead and multiply the x squared bit term times the z term, and I end up with x squared z plus x squared delta z minus 2x delta x z minus 2x delta z. Well, yet again, if you've got a delta times a delta, that term's going to go away. It's basically 0. So this next line is approximating those deltas going to 0. So then you have x squared z is equal to x squared z plus x squared delta z minus 2x delta x z. Okay? Now you have x squared z on both sides, so that subtracts and go away, and then you end up with z is equal to x squared delta z minus 2x delta x z. Okay? So since it's set equal to 0 and there's an x in every term, you can divide out by that, and you end up with 0 is equal to x delta z minus 2 delta x z. Well, now we have our equations for strain. Remember, strain in the x direction would be delta x over x, and strain in the z would be delta z over z. So if you rearrange this little equation right here, you can get delta z over z is equal to 2 delta x over x. Now if you take the ratio of these strains, you end up with 1/2 is equal to the strain in the lateral direction divided by the strain in the z. Okay, so that's why the threshold there for that Poisson ratio is 1/2, because it assumes that the volume is conserved. And it also explains why, you know, the Poisson ratio being greater than 0.5 isn't very likely. That would mean that the density increases, which doesn't happen very often. So you have these Poisson's ratios that are less than 1/2 because volume is never conserved, and actually when things get stretched out, you get void formations, and so the volume actually, total volume actually increases a little bit. Now there's other elastic properties. We talked about shear, okay, and we also talked about things that were under a stress where they're being compressed hydrostatically and otherwise. And so when you're measuring other things other than just tensile along the axis, then you have different moduli to talk about. Instead of the elastic modulus or the Young's modulus, you've also got your shear modulus. The shear modulus is often expressed with a capital letter G here. And then you have your shear stress, tau, is equal to your shear modulus G times delta, which would be your shear strain. Okay, so that's plotted here. You can also talk about elastic or bulk moduli. That's often symbolized with a K, okay? Now, since what you're doing for these sorts of materials is you're putting them under some sort of pressure change, usually like taking them down to the bottom of the ocean or filling them up with gas and applying an outward pressure, then oftentimes instead of a stress, we just put it in terms of the pressure that they're likely to experience. And so that's pressure, which of course is the same units as your stress. Pressure is equal to negative your bulk modulus times delta V over V naught. So it's easier, of course, with these materials to measure a change in volume than it is a change in the dimension in any one particular way. So that's how it's often expressed. You can get these special relationships for isotropic materials. That would mean that it would expand and contract in all directions sort of uniformly, sort of a homogeneous expansion and contraction. If that's the case, then you can relate your shear modulus to your elastic modulus in this way, in this relationship given here, G is equal to E over 2 times 1 plus nu. Or for the bulk modulus, K is equal to E over 3 times 1 minus 2 times nu. So you can put those relationships in. I'm not going to derive those. They're, if you want to look it up, there's these relationships here. I do want to mention, though, that a lot of materials are not isotropic. You've got your crystalline directions, you've got your crystalline faces, and of course some directions are more densely or tightly packed than others, and so oftentimes materials like to expand along one dimension but not others. And so oftentimes materials are not isotropic for that reason. Let me do another example problem for you. Here you have a cylindrical bar of steel, 10 millimeters in diameter, and it's to be deformed elastically by application of a force along the bar axis. Determine the force that will produce an elastic reduction of 0.003 millimeters in diameter. For steel, the elastic modulus is 207 gigapascals, the shear modulus is 83 gigapascals, and Poisson's ratio is 0.3. Okay, so they threw a lot of red herrings at you here. You don't necessarily need all the information that you're given. Along the bar axis, that means that it's a tensile stress and not a shear stress. So they gave you the shear modulus, but you didn't really need it, okay? Also, you're given that radial change, but in your formula for the tensile stress, what you need is your stress, or your strain, I'm sorry, along the axis and not that radial. So you need to use your Poisson's ratio to figure out what your change in Z would be, what your strain in Z would be. Okay, so we're going to use the Poisson's ratio. Epsilon r over epsilon z is equal to 0.3, but I'm going to rearrange that so that I can solve for what my strain in the z direction would be. So given that, I get my radial strain is 0.003 millimeters divided by 10 millimeters, and then divide that by 0.3, and then I get a strain in the z of 0.001, okay, using my Poisson's ratio. Now that I have the strain in the z direction, then I can use my formula for the stress. So I have stress is equal to my elastic modulus E times my strain epsilon, and that's equal to 207 gigapascals times 0.001. Now, remember, my stress is my force divided by my cross-sectional area. Here that's F over pi times 5 millimeters squared, all right? And then I can solve for my force, and I get 16,260 newtons. All right, so that's how to approach that problem. We've been talking a lot about our elastic or our Young's modulus, so let's just look at sort of a comparison of different kinds of materials and how those moduli compare. So remember, your elastic or your Young's modulus is kind of how stiff your material is. It's related to the material stiffness or how resistant it is to an applied stress. So going up here, you have stiffer materials that are more resistant to change. Now, they're grouped here, metals in the first column, ceramics, graphite, semiconductors in the second column, polymers, and then composites. So here we have unsurprisingly, I guess, if you compare your metals to your polymers, you'll see that your metals are much more resistant to an applied stress than a polymer. That just makes sense. I mean, I can deform a rubber band and some plastics with my bare hands, right? I can just stretch those suckers right out, and I can make them plastically deform and stretch. Rubber band's perfect example here. Much more difficult, though, to do that to a wire, okay? So my metals and alloys are a lot stiffer than my polymers. What might be a little surprising to you is that the stiffness or modulus for the ceramics is actually comparable and in some cases even larger than the stiffness of metals. Okay, and as we'll see and discuss, yes, these things are very stiff, they're very resistant to changes, and they also break like crazy. So you can get a metal to stretch out, you can draw a metal into the wire, not so much, say, quartz, okay? If you take a rock and you try to stretch that sucker out and draw it into a wire, you start stretching it, it'll just break, okay? So there's a big difference between an elastic modulus and then how resistant something is to fracture. These materials, these ceramics, are very resistant to a small pull, and if you pull them too hard, they just fracture and break. Unsurprisingly, if you look at your composites, they're kind of a mix. They have a very large range of what their elastic modulus can be, and it just depends on the material. And this is, of course, because you're taking these materials and you're blending them together. So you might take a polymer, for example, and blend it with a metal, and of course that's going to increase the possible range that you've got for your elastic modulus. All right. Here's some more useful elastic relationships that you might need in your homework or if you go out into the world with some engineering problems. These relationships for simple tension here are just giving you what your maximum deformation is in terms of the stress and the initial length in the modulus. So here, remember that your strain, this is your deformation, and your strain would be your deformation divided by that initial length, okay? And then this force over area, that's just your stress, okay? So this is just sort of a rearrangement of that equation. And then here's a rearrangement of that equation for the lateral deformation. All right, and then for torsional relationships, yet again, same kind of idea. This is the angle of the twist, and we're just putting that in terms of the moment of the material, the initial length, the dimensions of the material, and of course the shear modulus. All right. Okay, well, I hope that helps, and if you have any questions, please let me know.